Okay, there we go. All right, so today we're going to be talking about infinity. We're going to be looking at section 4.6, which is, a few chapters down the line, but I don't know why it's in chapter 4. It's perfectly good. It fits perfectly well with chapter 2, so I don't know why they don't just put it in chapter 2. So we're going to be talking about limits involving infinity, both what are called infinite limits and limits at infinity. We'll go over the difference between those two things. So let's start there. So an infinite limit is a limit I guess an infinite limit is, I'm going to put this kind of informally, is where the output, I guess you could say the limit doesn't exist because the y values are approaching plus or minus infinity. Let's start with that. So an example of this would be something like the limit as x approaches 0 of 1 over x squared. This is a classic example. It helps to have the graphs of functions like this kind of in mind. Okay, so right over here, I'm going to bring in a Desmos. What does 1 over x squared look like? It looks like that. Does that look familiar? Kind of looks like a hyperbola, except that the two legs of the hyperbola are like both on the same side of the x-axis, and they're kind of going up like this. If we imagine what happens to y values as x values approach 0, then it becomes very clear what's going on here, right? Let's build a little table of values. If you go like 0.1, you get 100. What we're doing is reciprocating and squaring, right? 0.01, you get 10,000. Yikes. 0.001, a million, right? So what's happening as you get closer to 0, at least from the right-hand side, is that the y coordinates are exploding, right? Getting bigger and bigger and bigger. Similarly, from the left-hand side, if I just go through here and put negatives on everything, it doesn't actually change the y outputs because we're squaring the x values. So whether it's positive or negative doesn't matter, right? So in this case, we can say this equals infinity. Contrast that with limit as x approaches 0 of 1 over x. If it's just 1 over x, then from the right-hand side, you approach infinity, but from the left-hand side, you approach negative infinity. So if I take away the squaring down there in the denominator, now these are not approaching the same infinity, right? We've got different infinities, the plus and the minus. So this is, I guess, I would usually instruct you to answer this with our abbreviation, our initialism. DNE does not exist. Oops, sorry. Every time I touch the mouse, I'm in danger of accidentally zooming in. That was what happened there. Sorry. Okay. Let's look at a couple other examples. The limit as x approaches 0, specifically from the right-hand side of the natural log of x, is an interesting one. What happens if you evaluate the natural log of 0? What is the natural log of 0? Kind of a trick question, right? Anyone remember the natural log of 0?
Isn't it undefined?
It is undefined. Yeah. Natural log of 0 is undefined. The reason being, if you tried to do ln of 0, if that was equal to some number, let's call it a, then this would mean that e to the power a equals 0, right? But no matter what a you pick, no matter what that number you raise e to the power to, you're never going to like get 0 out of that, right? This is impossible. So that's why this is also impossible. You can't have the log of 0. So yeah, so log of 0 is undefined. But what's the limit as x approaches 0? Now I said from the right-hand side right here because we only positive x values allowed. In the natural logarithm or any logarithm. Do you remember that? How a logarithm's domain is just positive numbers, doesn't allow negative numbers. So the reason for that is, again, because if you look at e to the power something, you're never going to get a negative number out of that. You only ever get positive numbers by raising e to some power. So what does it do? Well, if we look at the graph, so if you hang on. Actually, something that happens a lot is if you graph this on a TI, you get something really not useful at all. On a TI, you get a graph that looks sort of like that. And what exactly is happening at 0 is unclear because the graph just sort of stops shy of 0. It doesn't actually make it to 0. Like, it literally just sort of graphs it to about here, and then it sort of stops. And then there's this question of like, well, what the heck happens down here? It's very unclear based on this picture what happens down here. This is because TI calculators suck. To be completely blunt, they just can't graph. They just can't even graph something that's close to a vertical line. It's silly. I don't even know why. You'd think that, in 50 years or whatever, they would have figured out how to do that. It's 2023, right? So, sorry, I don't like TI calculators. Desmos gives us a much better picture of the natural logarithm, right? What does the natural logarithm look like? It looks like this, right? The reason TI calculators can't graph this is because it's close to a vertical line. It's like a vertical asymptote is what's happening over here, right? As x gets close to 0, from the right-hand side, the natural logarithm shoots down towards negative infinity. So this is another example, negative infinity here. This is another example of an infinite limit. Okay. There are lots of other examples. When you studied rational functions, you learned that if the denominator is equal to 0 at some x value, but the numerator is not, then you have a vertical asymptote. So like, for example, if you have something like x plus, back this up here, you have something like x plus 2 over x minus 5, this is going to have a vertical asymptote at x equals 5, right? Because your because the denominator is approaching 0, and so in general, when the denominator is approaching 0, you're dividing by like really, really small numbers. If the numerator, though, is approaching something other than 0, any other number, any other constant other than 0, like in this case, the numerator is approaching 7, right? Because it's 5 plus 2. Anytime you have the numerator approaching some non-zero constant and the denominator approaching 0, you have a vertical asymptote. Okay. Now, whether we can answer this limit question with like an infinity or minus infinity kind of depends. It goes back to this distinction between these two cases again, something like that, where if you have the factor that is causing the denominator to be 0, if it has an odd multiplicity, then you're in this case. The odd multiplicity case is like 1 over x to the power 1. So in this case, in what I've drawn, in like the example I've written down here so far, the correct answer here would just be does not exist, because this is similar to the 1 over x case, where the vertical asymptote is a vertical asymptote because it's going like, it's this picture. You see what I'm doing with my hands here? It's like it goes to positive infinity on one side and negative infinity on the other. But if you have an even multiplicity case, then you can end up with, like, say if this is squared, or maybe to the power 4, something like that, then you can actually end up, then you end up with either a plus or a minus infinity. And it depends on the other parts of the function. So like in this example, my numerator is approaching 7, my denominator is approaching 0 with an even multiplicity, right? The power 4. So then this is going to be positive infinity, because we've got a positive number divided by positive numbers that are close to 0. On the other hand, if we had something like, if we edit this slightly, actually, let's just do a separate example and change it ever so slightly. Let's keep the denominator the same, some even multiplicity of a factor that gives us 0. And there could be other factors in the denominator, like you could have x plus 2 or, you know, anything else down there. Okay. As long as you have some factor that's approaching 0, the whole thing is going to be 0, right? Because 0 times anything is 0. 0 times any constant, at least, is 0. So the difference is if you had like, if we threw in a negative here, okay, if I just throw in a negative sign there, then we can see that now the numerator, instead of approaching 7, is going to approach, let's see, -5 plus 2 is -3. And our denominator is still approaching 0, but with positive numbers. You can write that. You see how I've written denominator and then arrow 0. This means denominator is approaching 0. I can use my little plus superscript to mean from the right-hand side. So in the case of approaching 0, that would mean like, you know, that little plus there would indicate that we're talking about positive numbers getting closer to 0 only, right? So now in this example we're still going to be approaching infinity or negative infinity because we've got the constant divided by something getting close to 0. But because the constant in the numerator is negative and the numbers in the denominator are positive, overall, we're talking about negative numbers. So what this is approaching is negative infinity. Okay, so we just have to pay attention to the signs, right? What are the numbers? Are we talking about negative numbers? Or are we talking about positive numbers? It can even help to like plug in some examples, look at it numerically or look at it graphically. Okay. There's a comment in the chat to sort of sum up what I've been saying. Yeah, we can have limits, infinite limits. We can sometimes have a limit be positive infinity or negative infinity, but only if it is, you know, we're talking about a two-sided limit, only if it's doing the same thing on both sides. If you ever have it approaching both positive and negative infinity on the different sides, then we do not say that the limit is positive or negative infinity. We just say DNE because they don't match. Yeah. So all of this is still about x's approaching some finite value. If we go through here and we look at what the x's were approaching, here we had, like x approaching 0. Here we had x approaching 0. Here we have x approaching 5. We could have done any other constant number. That stuff is all still x approaching a constant finite number. The other thing to talk about is limits at infinity. Limits at infinity occur when the x value is approaching positive or negative infinity. Okay, so this is related to what we call end behavior. You guys remember that term from pre-calculus? End behavior. It's also related to horizontal asymptotes. We had vertical asymptotes with infinite limits, but with limits at infinity, we can have horizontal asymptotes. So horizontal asymptote is a type of end behavior, but there's other types of end behavior. When you were in pre-calculus studying polynomials, you probably talked about how if you look at, like, let's say you look at x to the power something, and that x to the power something has the end behavior is like whether it's going up or going down. And with polynomials and power functions like this, it's always going to be infinity or negative infinity. So here with just y equals x, we have negative infinity on the left and positive infinity on the right. But then you get this sort of like even power, like x squared is positive on both sides, and then you got negative on both sides, or negative positive again, and then it kind of alternates like this. Remember this kind of discussion about the end behavior is just kind of describing, is it going up or going down? And then it also depends on whether you have like a negative or a positive number as your leading coefficient. You have a negative leading coefficient, then it flips the end behavior. That all sound familiar? So that end behavior, that's what limits at infinity are examining. Okay, so in all of these cases of end behavior, we can express all that in terms of limits. So for example, we could say the limit as x approaches, say, infinity of x to the power 3 is infinity. That's a positive infinity. But the limit as x approaches negative infinity of x to the power 3 is negative infinity. And that's because x to the power 3 goes up on the right and down on the left. All right? If it was like x squared, then they would both be positive infinity. If it was like negative x squared, they would both be negative infinity. That kind of thing. So this is end behavior, right? Limits at infinity are describing end behavior. Now, sometimes you have a limit at infinity, which is like finite. So for example, the limit as x approaches infinity of 1 over x, what do you think that is? It's the end behavior of the 1 over x function. If we imagine making a table of values here, we can, say, okay, well, we want x to go to infinity, right? So x f of x. Here, let's make a little table of values horizontally. Pick a big x value. Let's start with 10. Not very big, but let's start with 10. F of x is 1 over 10, or 1/10. Let's pick a bigger x value, like 100. F of x is 1 over that, so 1/100th. Bigger x value, 1/1000th, and so on, right? And what we can see here is that as the numerator approaches infinity, our denominator is approaching 0. Right? So this is an example of a function with a horizontal asymptote at y equals 0. In general, horizontal asymptotes are defined by this situation. If the, actually, it doesn't make sense to write this one with text here. I'll write it this way. Our definition of a horizontal asymptote is actually this. If the limit as x approaches either plus or minus infinity, you can do either one. If that of a function is ever equal to a L, where L is a finite value, then the horizontal line y equals L is a horizontal asymptote of the function f of x. Okay. Whenever the end behavior on either the left side or the right side is finite, whenever the limit at infinity is a finite value, that's a horizontal asymptote. So let's look at another example. I'm going to export this. Oops. New sketch. Another example of a function with a horizontal asymptote is e to the x. What do you think the limit as x approaches negative infinity of e to the power x is? Okay. Let's remember what e to the x looks like. It looks like this, right? So e to the x on the left side is kind of coming down and getting closer and closer to the x-axis, but it never crosses over the x-axis, right? If you take your calculator and you start asking for, you start plugging in like numbers like -10, you get e to the -10. E to the -10. I'm just gonna do a calculator on my over here on my other screen. This is just typing it into the Google search bar. Like I said, my second favorite calculator. E to the -10 is like 0.00005 ish. And then if you plug in like -100, you get something even worse. E to the -100 is like 3.7 times 10 to the -44, which is a very, very small number, close to 0. So as we're approaching negative infinity here, this is getting close to 0. This is 0. We have a horizontal asymptote at 0 because the left side end behavior is the limit is 0. Okay. The right side end behavior, by the way, infinity, isn't it? These are two very specific limits that you should really memorize. Actually, here, let's kind of color code them. The red one there and the blue one there and the red one here. Okay, those are two very specific limits that I recommend memorizing. And similarly for logarithms. So that's for exponential functions, and for logarithms, we'll do those as well. So the other ones you should memorize are this guy we went over earlier. That would be, this area down here for the logarithm. Okay, and then the limit at infinity of natural log of x. What's going on over here? What happens to the logarithm function as x gets bigger and bigger and bigger? Let's look at our graph again. Here's natural log of x. Here's the logarithm function. This is the natural logarithm, right? What do you think's happening here? What appears to be happening? It's a tricky one.
It's increasing very slowly.
Thank you. That's right, Zeki. It's increasing very slowly. So looking at the graph is like actually almost deceptive here, because it looks like there might be a horizontal asymptote, right? It really looks like there might be a horizontal asymptote. It looks like it's sort of capped off by something. Like it looks like a horizontal line out here, but it is not. It actually does not have a horizontal asymptote. This graph just goes to infinity. It shoots off to infinity. And how do we know that? One way we know that is that this graph is, these two functions, natural log of x and e to the x, are inverses of one another. And so from pre-calculus, these are reflections of one another over this diagonal line, right? If the natural logarithm had some sort of horizontal asymptote, say at 4 or something, right? If there was some sort of horizontal asymptote that this was getting close to, like this, okay? If there were, then that would mean that the e to the x graph would have a vertical asymptote at the same exact number. But does the e to the x graph have a vertical asymptote? No. I mean, you can plug in, you can do e to the power 1, e to the power 2, e to the power 3, e to the power 4. E to the power 4 equals 54.6 approximately, right? So this isn't a vertical asymptote. It's just a point on the graph up here at 54.6. It's a point right there, right? There is no vertical asymptote on e to the x. And so therefore, there is no horizontal asymptote on natural log of x, since they're basically the same graph, just reflected over, right? So that's really important pre-calculus background that we're going to be leaning on heavily here. All that, knowledge about these functions. Okay, so this one is infinity, despite the fact that it looks like a horizontal asymptote. It really is just increasing, as Zaki said, very slowly. So there's a couple of key things to memorize. So Another like sort of fact that we can really lean on is the following one here. If you're looking at the limit as x approaches either plus or minus infinity, and you're looking at a constant divided by some power of x, and that can be any positive rational power. So that means, so it has to be positive, first of all, because we want it in the denominator. If it was a negative power in the denominator, then we'd actually flip it back up to the numerator. Remember how that works with negative exponents? Like the negative kind of makes them, negative exponent makes it flip, whether it's in the numerator or denominator, it causes a reciprocal operation. So that's why it says positive. And then rational, it just has to be rational. Actually, I think this might be true for irrational exponents as well, but irrational exponents are just kind of weird. So let's just not touch them. But rational means that this is true for, any positive integer, but also things like a half, positive fractions, right? Or like 3/8 or whatever. Okay, so fractional exponents. Remember that x to the power 1/2, for example, is the same as the square root of x, and any other fractional exponent can be interpreted as a root combined with a power. And I wrote the wrong number. That was 3/8, so I should write the 8th root of x cubed. Okay, so radicals also, this applies to them. So basically, whenever you have a constant in the numerator and some power of x in the denominator, as x approaches plus or minus infinity, this limit is always going to be equal to 0. And the reason for that is that power functions all grow. Power functions, they always grow, whether it's square root of x or x to the 1 power, x to the 2 power, x to the 100 power. They're all growing functions. And so if your numerator is constant and your denominator is growing bigger and bigger and bigger and bigger, the reciprocal of those big numbers is going to be approaching 0, always. So that's another really nice sort of like key fact to lean on here. Okay. Another one we can memorize. So now let's look at some examples where we're going to use these ideas. Oops. So first, let's look at a rational function. Let's look at the limit as x approaches infinity of sorry, I got distracted by something. I think, well, I don't know. I think it's fine. X minus, let's do like x squared plus 2x minus 5 over 3x squared minus 7. Okay. So when approaching a more complicated rational function like this, one thing that's tempting to do is to try to apply like the limit properties. Okay, if you attempt to apply a limit property, the one that says limit of like f of x divided by g of x is equal to limit of f divided by limit of g. Okay, if you attempt to apply that property, what we get is the limit of x squared plus 2x minus 5 divided by the limit of 3x squared minus 7, x going to infinity in both cases. Okay, that is splitting the limit across the division, right? Which normally is a valid thing to do, provided the limits both exist and the denominator isn't approaching 0. If the denominator were approaching 0, we would have a different situation. But this is provided the limits both exist. Now, the problem here is that since we're doing limits at infinity of, in each case, the numerator and denominator, each of these is a polynomial. Polynomials end behavior is always infinite, either positive infinity or negative infinity, depending on, right, which direction you're going and depending on that leading coefficient. Remember all those rules I talked about earlier? That stuff from pre-calculus. So in this case, we're talking about quadratic polynomial functions, so degree 2, as x approaches positive infinity, and both of them have positive leading coefficients. So pretty straightforward situation. They're both approaching infinity. But what the heck does that mean? Okay, well, remember I introduced this term indeterminate. Well, it turns out the idea of an indeterminate situation does not only apply to 0 over 0, it also applies to infinity over infinity, as well as a number of other things which we will encounter throughout this semester, like 0 times infinity, infinity minus infinity, 0 to the power 0, and a few others, etc. There's a couple others. So these, it turns out when looking at a limit, anything of any of these formats, these are called indeterminate forms. So so we had 0 over 0, now we've got infinity over infinity. What it means is that this is just not really a valid approach. This isn't really going to give you any conclusive information about this limit. So I would say this is an invalid strategy here, right? And you know, this property that we were trying to use, it did say you can use this provided the limit of the numerator and the limit of the denominator both individually exist. But if the limits are infinity, technically that means the limit doesn't exist, right? So that's why. So yeah, it wasn't really valid to begin with to even try to do that. So instead, we can, like before, apply some algebra to manipulate this expression until we can apply those limit properties. Okay, so here's what we can do. We can take this here and we can multiply the numerator and the denominator by something that's going to change the format of this expression here. So we're going to multiply by 1 over x squared in both the numerator and the denominator. Of course, maintaining the value of the expression so that we don't change the function at all. We're just going to change the way it's written. We're not going to change what it is. It's still the same function. In other words, it's equivalent. Okay, so we're multiplying by 1 over x squared. We're then going to distribute that multiplication by 1 over x squared across all of the terms in both numerator and denominator. And when we do that, we're then going to sort of simplify the results. So we're going to get like x squared over x squared plus 2x over x squared minus 5 over x squared. 3x squared over x squared minus 7 over x squared, like so. Now, simplifying, we can see there's lots of cancellation that's going to go on here. X squared over x squared is going to cancel out. 1, right? One of these x is going to cancel with one of those. So we're going to get like plus 2 over x And then I guess there's no simplifying we can do on the third term. And then in the denominator, we also have this simplifying right here. So we have 3 minus 7 over x squared. Okay. Then, now that we have done this small algebraic manipulation, now if we try to apply the same limit properties that I was trying before, right? We split the limit over the division. And then in turn, we can split the limit over the addition and subtraction. Got one more step to plug in here. So we have limit of 1 plus the limit of 2 over x minus the limit of 5 over x squared. Sorry about the noise. Do you see what's going to happen here? Before we did this little algebraic manipulation, we had infinity over infinity, and it was not valid, right? It was indeterminate. But now that we did that little algebraic manipulation, look at all these little limits. These are all x going to infinity, right? All of these ones fall into this case, where they're all a power of x in the denominator and a constant in the numerator. All of those limits are equal to 0, right? So that's equals 0, that's equals 0, and that's equal to 0. So they're all 0, but then we have these two limits at the beginning, which are limits of just constants, right? Limit of 1 and limit of 3. Do you remember what the limit of a constant is?
Just the number?
Yeah. So this is equal to 1, and this is equal to 3. So now evaluating all those, we get 1 plus 0 minus 0 over 3 minus 0, and the whole thing is 1/3. And we have our limit. Okay. Now, so that is an approach that you can use for any rational function. What you can do is multiply by 1 over the highest power of x. And generally, you actually want to pick the highest power of x that appears in the denominator, so that you don't accidentally end up with a denominator approaching 0 when you're done. You don't necessarily want that. The best way to go about it is the 1 over the highest power of x that appears in the denominator. There's a question from Hannah. Do you mean the limit? I'm not sure exactly what you mean. Do you mean like what limit are we doing? Like what is x approaching? Is that what you mean? X approaches number? Yes. Yes, always the same. Yeah. So when you are applying these limit properties of like sort of splitting limits up over division or addition or subtraction or multiplication, it always is the same limit, x approaching the same number. There we go. So another question in the chat real quick. Why is the limit of 2 over x equal to 0? Whenever you have the limit of a constant divided by a power of x, that's always going to approach 0. Basically, it's 2 divided by big numbers, right? And as the numbers get bigger and bigger and bigger, right, as x gets close to infinity, you're dividing 2 into more and more and more pieces, which is going to give you smaller and smaller and smaller pieces, right? So 2 divided by 100, 200ths is 0.02. 2 divided by 1,000, even smaller, right? The size of those individual pieces you get through the division would be increasingly small. So that's why it's approaching 0. Yeah, we're out of time. The very last thing I'll say is that you guys probably learned like a rule for how to figure out the horizontal asymptote of a rational function. And so you might have known the answer to this before we even started, just because you might remember that the result was going to be the ratio. So when the degrees of the polynomials match each other, the horizontal asymptote occurs at the ratio of leading coefficients. Was anyone thinking about that? Yeah, a few of you. Yeah. Yep. So that is basically a shortcut. What I want you to do in this class is not rely on that shortcut and instead practice doing it this way that I've shown you, because this is a more rigorous approach to proving that limit. The shortcut you learned in pre-calculus is correct, but I want you guys to now have the experience of like working through the details yourself so you can understand better why that shortcut is correct. Okay, so you'll be doing that in your homework. All right. Have a great weekend, everybody. Happy studying. Remember that that next assignment's due tonight. You'll be getting some feedback from me on, I think, Sunday. Okay. Bye, everyone.
Thank you,
You're welcome, Adam.
Professor?
Wait, how did you know it was me?